Hi ladies. So in this lecture video, we are going to be talking about the pH scale and pH calculations. So the pH scale is a logarithmic scale. Which means that a difference in 1 unit of pH, so pH is unitless, so a difference in 1 unit of pH, so if we have a pH of 2 to pH of 3, for example, we're going to see a 10 times difference in our concentration. So I'm going to do brackets C. So this could be our concentration of hydronium ions, specifically for pH, is what we're talking about with our concentration there. So it's a logarithmic scale, so we're going to be using your log button on your calculator. We're going to be doing inverse log, so 10 to the negative whatever, when we're doing these calculations. So aqueous solutions, so things that are dissolved in water, contain both hydronium ions and hydroxide ions floating around in solution. If we have a high hydronium ion concentration, so that hydronium ion is the same thing as a hydrogen ion concentration, but if it's in water, we're forming hydronium ions. So high hydronium concentration is an acidic solution. So we have a pH of less than 7. Acidic solutions have a pH of less than 7. If we have a high hydronium concentration, we're going to have a low hydroxide ion concentration with acidic solutions. For a neutral solution, our hydronium ion and hydroxide ion concentrations are going to be the same. So neutral solution, we got a pH of 7. And a high hydroxide concentration means that we have a basic solution. So we have a low hydronium ion concentration if we have a basic solution. Okay, so in table 14.7, we have a list of common substances and their pHs. So stomach acid, it has a really low pH, so it's very acidic, 1 to 3 on the pH scale. Things like soft drinks, they're pretty acidic, between 2 and 4. Water is 7. Blood is very neutral, and it's super important for it to be neutral, and we'll talk a little bit about that when we talk about buffers in the next video. And then a 4% sodium hydroxide solution has a pH of 14, so super, super basic. Okay, so let's do example number 12. So let's classify the following as acidic, basic, or neutral on the pH value. So if we have a pH of 4, we're less than 7, so this is acidic. If we have a pH of 13, we are greater than 7, so we are basic. And if we have a pH of 0.85, that is very acidic. So it is less than 7. Okay. The next thing that we are going to be doing is we're going to be doing some pH calculations using these 6 equations. So we, in a row, those 2 equations are related. So this first equation and this equation, they are the inverse of each other. We're trying to find pH here, but here we would know the pH and trying to find the hydrogen ion concentration. These 2 guys are related, but inverse. And then these 2 guys are related, but inverse. So the inverse of a log is 10 to an exponent, basically. Okay, so let's look at example number 13. Calculate the pH of the following solutions. And we're using this equation. They tell us which equation to use, so that's what we're going to use. So we are looking for the pH. So pH is equal to the negative log of this guy here, the hydrogen ion concentration that we're given. And if you put that in your calculator, you should get 3. And for B, Same equation, we're just doing the negative log of this guy, 0.0001 molar solution. If you put that in your calculator, you should get 4. If we're dealing with the number 1 with like logarithmic problems like pH, we're looking at how many decimal places we have basically, and that's bringing us back to here. A difference in 1 unit of pH, so here we have 3 and 4 down here. We're going to see a 10 times difference in concentration. So notice with 3, we've moved our decimal place over 1 to the left from 4. So that's talking about what we were talking about up here, the 10 times difference. All right, so example number 14, we're using another equation. So we're just plugging into this equation. We know the pH, so we're doing the times 10 to the negative pH. We need to do that negative. So here we have our hydrogen ion concentration is equal to 10 to the negative 2. And that is 0.01 molar hydrogen ion concentration. Same with tomato juice. We have 10 to the negative 5. And that is 0.12345 molar concentration. All right, with example number 15 and 16, we are using the same equation, but in number 15, we are looking for the hydroxide ion concentration. So we're going to do our hydrogen ion concentration, which we are given 10 to the negative 5 molar, times our hydroxide ion concentration. That's what we're looking for, so that's my variable, is equal to 1 times 10 to the negative 14. So we need to divide by 1.0 times 10 to the negative 5 on both sides so that we can isolate our variable. And we get a hydroxide ion concentration of 1.0 times 10 to the negative 9 molar. Remember, concentrations, we have units of molarity. pH is unitless. All right, example number 16, we are basically continuing on with that same equation. So this time we know the hydrogen ion concentration. So, no, we know the hydroxide, sorry. I can read. Here we go. So 1 times 10 to the negative 3 molar is equal to 1.0 times 10 to the negative 14. Sorry, there's no units there. Okay, so let's divide 10 to the negative 3, 10 to the negative 3, and we should get a hydrogen ion concentration of 1 times 10 to the negative 11. Also notice with our exponents, we could have subtracted them. That is because we have the same base. We have the base of 10. We just have to be careful about these numbers here. If they are anything but 1, we got to be really, really careful about subtracting these. But because these are 1, we could subtract them and get negative 11. Okay, let's look at example number 17. So what is the pH of the solution if our hydroxide ion concentration is 4.0 times 10 to the negative 11 molar? This is a multi-step example, which means we are using more than one of these equations here. So we're given a hydroxide ion concentration. So we could, we have a few options here. In order to find the pH, we could, we either need a hydrogen ion concentration or we would need a POH. So there's 2 ways we could do this. I'll probably show you both ways. So I'm going to do, use this first equation here. So I'm going to do my hydrogen ion concentration. I'm going to solve for that and then use that to find my pH. Times 10 to the negative 11 molar is equal to 1.0 times 10 to the negative 14. So we are again dividing by 4.0 times 10 to the negative 11 on both sides. And we get a hydrogen ion concentration of 2.5 times 10 to the negative 4 molar. At this point, we can use our pH equation. So now that we know hydroxide ion concentration, we can solve for the pH. So pH is equal to the negative log of this guy here, 2.5 times 10 to the negative 4 molar. And we get a pH, so with 2 sig figs, of 3.6. Your other way of doing that, it's going to look something like this. So we're going to use our hydroxide ion concentration to solve for POH. So we would do POH is equal to negative log of 4.0 times 10 to the negative 11. And I don't have that. Negative 11. Okay, so that's going to give us a POH of 10.39 blah, blah, blah. Because there are a few decimal places, so we're not rounding to the very end. At this point, we're going to do our pH plus 10.39 blah, blah, blah is equal to 14. So we're going to subtract 10.39 blah, blah, blah on both sides to isolate our variable, and we will get a pH, so 14 minus second answer, of 3.6. Either way works. Notice how there were 2 pathways we could have taken, and we both get the same answer. So at this point, you can do the worksheet on pH calculations.